In this video, I will be discussing about the joint probability distributions for both the discrete random variables and also for the continuous random variables. Now, in reality, there are several situations where we may realize that it is sometimes desirable to record the simultaneous outcomes of several random variables. Take for example, in a study to determine the likelihood of success in college, the student's IQ, his grade point average in high school, and his study habits are considered. Thus, his success in college is a function of these three variables: his IQ, his grade point average, and his study habits here. And in this video, we shall be concerned first with the bivariate case, that is, with situations where we are interested at the same time in a pair of random variables defined over a joint sample space. Although in the next succeeding videos, we shall extend this discussion to the multivariate case, covering any finite number of random variables. Now, let's proceed to our definition 10. The function f of x and y is a joint probability distribution or the joint probability mass function of the discrete random variables x and y if the following conditions are satisfied. Number 1. The function f of x and y is greater or equal to 0 for all possible pairs of x and y. In other words, all probability values for each possible pair of x and y is never negative. Number 2, that the sum of all probability values for all possible pairs of x and y must be equal to 1. Number 3, that the probability of your random variable x whose value is equal to small x and the random variable y whose specific value is the small y is equal to the joint probability function of the small f of x and y for any region A in the xy plane, where A is the set of all possible pairs of the random variable x and y. Now, technically, a joint probability distribution for discrete random variables can be represented by a cross-tabulation of the two discrete random variables x and y. And this is illustrated in the table below. So you see here, our first random variable, which is x, we have the values of x sub 1, x sub 2, x sub 3, and so on and so forth until we reach to the last value of x sub m. And also our second random variable, which is y, has values of y sub 1, y sub 2, y sub 3, up to the last value of y sub n. So if you have this small f of x sub 1 and y sub 1, this is the probability value for the random variable x sub 1 and the random variable y sub 1. So this is the probability value of the pair of random variables x sub 1 and y sub 1. Also, this one is the probability value of the pair of the random variables x sub 2 and y sub 1. And also this one is the probability value of the pair of random variables x sub 3 and y sub 1. And so on and so forth. We have here the probability value of the pair of the random variables x sub m and y sub 1. So if you add all these probability values in this first column, we have the sum, which is f sub 2 of y sub 1, because you are adding across all x's here. And as shown in the table, the random variable x can assume one of the m values from x sub 1 up to x sub m, and the random variable y can assume any one of the n values from y sub 1 to y sub n. So the probability of the event that your random variable x will have a specific value of x sub j and your random variable y will have specific value of y sub k is given by this joint probability mass function of the small f of x sub j and y sub k. And specifically, the probability that your random variable x will have a specific value of x sub j is obtained by adding all entries in the row corresponding to x sub j, and is given by this formula that the probability of your random variable x having a specific value of x sub j is equal to f sub 1 of x sub j, which is actually adding across all y's here from k, which is equal to 1 to n. So if this is our x sub j here, this is our probability of our x sub j y sub 1. This is also our probability of x sub j y sub 2. Also, this is the probability of x sub j where y is y sub 3, and so on and so forth until you will reach this probability of x sub j where your y is y sub n. So adding all of these probabilities, this is equal to the probability f sub 1 of x sub j, because we are adding across all y's from y sub 1 to y sub n. And similarly, the probability that your random variable y will have a specific value of y sub k is obtained by adding all entries in the column corresponding to your y sub k, and is given by this formula that the probability of your random variable y having a specific value of y sub k is equal to f sub 2 of y sub k, which is actually adding across all x's here. And this can be illustrated in our table here. Suppose this is our y sub k. So at this cell, this is the probability of x sub 1 and y sub k. Also, this is the probability of x sub 2 and y sub k. And the next is the probability of x sub 3 and y sub k, and so on and so forth until you will reach this cell, which is the probability of x sub m where y is y sub k. So adding all of these probabilities, this is equal to our f sub 2 of y sub k, because we are adding here all probabilities across all x's here, but having the same random variable of y sub k. That is why we are just labeling this one as our second function of f, because this is just adding all probabilities across all x's. Now, since the probabilities of f sub 1 of x sub j and f sub 2 of y sub k are obtained from the marginal totals of the table, then we often refer them as the marginal probability functions of the random variables x and y respectively. And it should be remembered that the sum of all probability values of x sub j from j1 to m across all y's must be equal to 1, or adding all probability values of all y sub k, where k is from 1 to n, adding across all x's, the sum must be equal to 1, which can be written as the double summation of all probability values of x sub j adding from 1 to m and y sub k adding from 1 to n must be equal to 1. Thus, the above statement is the mathematical statement that the total probability of all entries is 1, which can be seen in the lower right-hand corner of the table, the grand total, which is this one here. Now, let us illustrate that concept in an example. 2 textbooks are selected at random from a shelf that contains 3 mathematics books, 2 statistics books, and 3 physics books. if the random variable x is the number of mathematics books and the random variable y is the number of statistics books actually chosen, find the probabilities associated with all possible pairs of values of random variables x and y. Letter B. Find the probability value for all possible pairs in the set A, where A is the set having all possible pairs of x and y whose sum is less than or equal to 1. Letter C. Find the one-dimensional probability distributions of x alone with values g of x. Letter D. The one-dimensional probability distributions of y alone with values h of y. And solving for our probabilities associated with all possible pairs, we have this possible pair of values of x and y as 0, 0 when you have all physics for the two books selected here. So no mathematics book, no statistics book. That's why the value of our random variable is 0 for mathematics, 0 for statistics. So if you have a value of 0, 1, it means that no mathematics book, but you have one statistics book. And in the pair of 1, 0, you have one mathematics book and no statistics book. Then therefore, the other book must be a physics book here. And this 1, 1 is one mathematics book and one statistics book. And in the pair of 0, 2 means that both of the books are statistics books here. And the pair of 2, 0 means that both of the two books are all mathematics books. So therefore, we can create our contingency table for our probability values. And you notice that your random variable x are 0, 1, and 2 because these are the possible values of your random variable x here, which is found in the first number in this ordered pair. And your random variable y are having values 0, 1, and 2 because these are also the possible values of your second number in this ordered pair. So solving for the probability values for each possible pair, we need to formulate the formula for the joint probability mass function. And the joint probability mass function of f of x and y is equal to the combination of 3 taken x at a time, because this 3 represents to the 3 mathematics books, and this is multiplied to the combination of 2 taken y at a time, because this 2 represents to the 2 statistics books, and this is also multiplied to the combination of 3 taken 2 minus x minus y at a time, where x is the number of mathematics books and y also is the number of the statistics books. And this will be divided by the combination of 8 taken 2 at a time, because all in all there are 8 books here, and you must have to choose 2 books at a time. And take note that the sum of these x and y must not be greater than 2, since you will be choosing 2 books at a time here. So solving for our first probability, we substitute that one to our density function of 3 taken 0 at a time, because you have the value of x which is 0, which means there is no mathematics book and there is no statistics book here. So this is combination of 2 taken 0 at a time, but your 2 books will be taken from the physics books. So this is multiplied by the combination of 3 taken 2 at a time. And solving for this one, this is equal to 3, because 3 taken 0 is 1, times 2 taken 0 is 1. So 1 times 1 is 1, and then multiplied to the combination of 3 taken 2, which is 3. So 1 times 3 is equal to 3 here. So that is why we have 3 over 28 as the probability value when your random variable x is 0 and your random variable y is also 0. Meaning, no mathematics book and no statistics book chosen from this set of books here. But when your x is 0 and your y is 1, we have our combination of 3 taken 0 at a time because there is no mathematics book, since x represents the number of mathematics books here. And 2 taken 1 at a time because your y is 1. And since there are 2 books here, your other book is taken from the physics books. So 3 taken 0 is 1, 2 taken 1 is 2, and 3 taken 1 is 3. So 2 times 3 is 6. So therefore, the probability value when your x is 0 and your y is 1 is 6 over 28. And in a reduced form, this is 3 over 14. But when your x is 0, which means that there is no mathematics book, but your y is 2, this means that the 2 books are all statistics books. So solving for the probability is to take the combination of 3 taken 0 at a time, but your 2 books must be taken from the 2 statistics books here. So therefore, there is no physics book. So multiplying this 3 taken 0, which is 1, and 2 taken 2, which is also 1, and 3 taken 0, which is also 1, the product is also 1. Therefore, the probability value when your x is 0 but your y is 2 is equal to 1 over 28. But when your x is 1 and your y is 0, we have to choose one mathematics book from 3 math books here. And your y is 0, so no statistics book, but you get the other book from the physics book. So therefore, if you multiply 3 taken 1, which is 3, and 2 taken 0, which is 1, times 3 taken 1, which is 3, therefore the product must be 9. So therefore, the probability value when x is 1 and y is 0 is 9 over 28. But when your x is 1 and your y is also 1, so 1 mathematics book and 1 statistics book, so therefore there is no physics book here. So 3 taken 1, which is 3, 2 taken 1, which is 2, 3 times 2 is 6 here. So therefore, the probability value when your x is 1 and your y is 1 is 6 over 28. And in a reduced form, this is 3 over 14. However, when your x is 2 and your y is 0, this means that your 2 books must be taken from the mathematics books here. Thus, you don't have statistics book as well as physics book here. So 3 taken 2 is 3, and 2 taken 0 is 1, times 3 taken 0, which is 1. So therefore, the product must be 3. Hence, the probability value is 3 over 28 when your x is 2 and your y is 0 here. Adding all probability values in the first column, we have the probability of 5 over 14, which is the probability when your random variable x is 0, adding across all y's. And also a probability of 15 over 28 when your x is 1, adding all probability values across all y's. And also, this is the probability value when your x is 2. Moreover, in similar case, we have a probability of 15 over 28 when your y is 0, adding across all x's here, and a probability of 3 over 7 when your y is 1, adding across all x's also here, and a probability of 1 over 28 when your y is 2. So this is the set of all probability values associated with all possible pairs of the random variables x and y. Now, let's proceed to our second question here. What is the probability value for the possible pairs of x and y where the sum must not be greater to 1? And to solve for this one, we need to identify the sum of the possible pairs that are not greater than 1. So we have this probability value because your x is 0 added to your y of 0, the sum is not greater to 1. And also this probability value because your x is 1 but the y is 0. So the sum of this x and y is not greater than 1. As well as this probability value when your x is 0 but your y is 1, since the sum of 0 and 1 is not greater than 1. Then therefore, we say that the probability of the sum of the two random variables which is not greater than 1 is equal to the f of 0, 0 added to the probability of 0, 1 and the probability of 1, 0. Because you see here that the sum of x and y is not greater than 1. And obtaining their corresponding probabilities, we have the probability of 0, 0, which is 3 over 28, which is found in the table here. And the probability of 0, 1, which is 3 over 14 here. And this will be added to this probability value of 1, 0, which is 9 over 28. Then therefore, adding these three numbers, we have the probability value of 18 over 28, which is having a reduced form of 9 over 14. So this is the probability value whose sum of the values of the random variables x and y must not be greater than 1. Now, let's proceed to our third question here. Find the one-dimensional probability distributions of x alone with the values of g of x. So, solving for the one-dimensional probability distribution of x, we need to add across all y's. So, we have g of 0, which is equal to the probability of 0y, wherein our x is always 0, adding across all y's. And you can see that these are the probability values of 0, 0 added to the probability value of 0, 1 here, and also to the probability value of 0, 2, because all their x's here are all zeros. So adding across all y's, we have a probability value of 5 over 14, which can be written here as 3 over 28 plus 3 over 14 plus 1 over 28. And making their denominators similar, we have the sum of 10 over 28, which is in the reduced form of 5 over 14. Now, let us solve also for the g of 1. And we have here when our x is 1 and our y is 0. Also, when our x is 1 but our y is 1. So, enumerating all of these probability values, we have f of 1, 0 plus f of 1, 1. And the probability values are 9 over 28 and 3 over 14. So, making their denominators similar, we have the sum of 15 over 28, which can be seen here in the table of 15 over 28. But we can also solve for our g of 2. And the g of 2 is of only one possibility, because this is when our x is 2 and our y is 0. So the probability value is 3 over 28. Hence, in a tabular form of the marginal distributions, these are the values of our g of x. The 5 over 14, which is our g of 0, and the probability of 15 over 28, which is for the g of 1, and the probability of 3 over 28 for the g of 2. In simple words, the marginal distribution of our x. So this is the column totals in the grid above there. Now, let's proceed to our fourth question. Find the one-dimensional probability distributions of y alone with values h of y. So showing our probability table, we have to solve our h of 0, and our h of 0 is having our y of 0 added to this probability value because the y is 0 but our x is 1, as well as the probability of 3 over 28 because this is having a y of 0 but the x is 2. So enumerating their probability values, we have the probabilities of 3 over 28 plus 9 over 28 plus 3 over 28. Adding the three fractions, we have 15 over 28, which can be found in this row total here. And also for our h of 1, when our random variable y is 1. And this can happen when your y is 1 but your x is 0, and also when your y is 1 but your x is 1. So enumerating these probabilities, we have the probabilities of 3 over 14 and another 3 over 14. So adding these two fractions, we have 6 over 14, which in reduced form is 3 over 7. But we can solve for our h of 2. And h of 2 happens when your random variable y is having a value of 2. And this happens in only one case here, because when your y is 2 and your x is 0, the probability is 1 over 28. Thus, in tabular form of the marginal distributions, these are the set of probabilities for all y's, that it has a probability value of 15 over 28 when your y is 0, adding across all x's. And it has also a probability of 3 over 7 when your random variable y is 1, adding across all x's, as well as a probability value of 1 over 28 when your y is 2, adding across all x's. But this happens in only one case. Then therefore, this marginal distribution of your random variable y is taken from the row totals here. So the numbers in the row total comprises the marginal distribution of y. Now, let's proceed to our definition 11. The marginal distribution of x, where x is a discrete random variable from the joint probability mass function of f of x and y. The joint probability distribution at xy is given by this g of x, which is the sum of all probability values of x sub j adding across all y's from 1 to n. And also the marginal distribution of y, where y is a discrete random variable from the probability mass function of f of x and y. The joint probability distribution at xy is given by this formula, h of y, which is the sum of all probability values of y sub k adding across all x's from 1 to m. So, as in the univariate case, there are several problems in which it is of interest to know the probability that the values of two random variables are less than or equal to some real numbers x and y. And this paves to the definition of the joint cumulative distribution of the random variables x and y. So, if the random variables x and y are discrete random variables, the function given by the big F of x and y is the probability value of your random variable x whose value is less than the specific value of the small x, and the random variable y whose specific value is less than or equal to the small y, can be solved by adding all probability values of your joint probability mass function of small f of s and t, where s are values of the random variables less than x, and t, which are the values of the random variables less than y, where f of st is the value of the joint probability distribution of the random variables x and y at s and t is called the joint cumulative distribution of the random variables x and y. And to illustrate this one in an example, we still use the same problem here. 2 textbooks are selected at random from a shelf that contains 3 mathematics books, 2 statistics books, and 3 physics books. And if the random variable x is the number of mathematics books and y the number of statistics books actually chosen, find the big F of 1, 1. So to solve this problem is to show again this table of probability values for this problem here. And to solve for the big F of 1 and 1 is the probability value of your random variable x whose value cannot be more than 1, and also your y whose values is not more than 1. So therefore, the only possibilities are probabilities of your random variables 0, 0, because your x and y are both not greater than 1. Also this probability value for 0, 1 and 1, 0, also 1, 1. Because looking at the values in the first number of the ordered pairs, we have numbers that are not greater than 1. And so with the second number in the ordered pairs. So getting their probability values for 0, 0, which is 3 over 28, and for 0, 1, which is 3 over 14, as well as the probability of 1, 0, which is 9 over 28. And the probability also of 3 over 14. So adding these 4 fractions, we need to make their denominators similar. So 3 plus 6 plus 9 plus 6 is equal to 24. So 24 over 28 is the cumulative distribution value for 1, 1. Or in reduced form, the value is 6 over 7. Now let's proceed to our definition 13 here. And this definition is the joint probability function for continuous random variables. So at this point, I will be discussing the joint probability distribution for continuous random variables. The function f of x and y is a joint probability distribution or probability density function of the continuous random variables of x and y if the 3 conditions are satisfied. Number 1, that the probability density function of x and y must not be a negative number for all possible pairs of x and y. Number 2, that the sum of all uncountably infinite pairs of the random variables x and y must be equal to 1. Number 3, that the probability value of the uncountably infinite pairs of the random variables x and y, which is an element of the set A, is the double integral of the joint probability density function of x and y over all the set A. And this can be illustrated in this example here. Cebu Normal University gives aptitude test in the sciences and humanities to all entering freshmen. If x and y are respectively the proportion of correct answers that a student gets on the test in the 2 subjects, then the joint probability distribution of these random variables can be approximated with the joint probability density function of k times the quantity of 2x plus 3y for random variable x from 0 to 1 and for the random variable y from 0 to 1 here. And it has a probability value of 0 elsewhere from the domain above. So find the constant k. Letter B, find the probability that more than 80% of the science test items and less than 50% of the humanities test items are correct here. So, solving for our constant k, we need to satisfy the second condition of our definition 13 in the previous slide, that the sum of all uncountably infinite pairs of the random variables x and y must be equal to 1. And this can be obtained by double integration here. So, the double integral of your joint probability density function of x and y is equal to 1. And we know that our joint probability density function is k times the quantity of 2x plus 3y. And this will be integrated with respect to x, where the limits of integration is from 0 to 1. And then with respect to y, whose limits of integration is also from 0 to 1, because these are the domains of their corresponding random variables. So integrating first our integrand with respect to x, we have the integral of 2x, which is 2x squared over 2. And the integral of 3y is 3y times x, because y there is considered a constant since our variable of integration is x. So 3y as a constant when integrated with respect to x, the answer is 3yx. And simplifying our answer, we have x squared plus 3xy. Then substituting our limits of integration for our x, we have 1 squared plus 3 times 1 times y minus the quantity of 0 squared plus 3 times 0 times y. So simplifying these powers, we have 1 plus 3y minus the quantity of 0 plus 0. And removing these square brackets, we have 1 plus 3y. And integrating this 1 plus 3y with respect to y, we have y plus 3y squared over 2, because the integral of 1 with respect to y is y. And the integral of 3y with respect to y is 3y squared over 2. So substituting our limits of integration, we have 1 plus 3 times 1 squared over 2 minus the quantity of 0 plus 3 times 0 squared over 2. So simplifying our numbers, we have 1 plus 3 halves. And adding this 1 to 3 halves, we have 2 plus 3 all over 2. So we have 5 halves times k, which is equal to 1. And then multiplying both sides of the equation by 2/5, we have the value of k, which is 2/5. So solving for our second question, we have to find the probability that more than 80% of the science test questions are answered correctly, and less than 50% of the humanities test questions are also answered correctly. So solving for our probability value of your random variable x from 0.80 to 1, because we are solving here the probability of answering the test items more than 80% in the science test. And then our random variable y is from 0 to 0.5, since we are after with the probability of answering the humanities test questions less than 50%. So this is the double integral of our joint probability density function of 2/5 of the quantity 2x plus 3y. And this will be integrated first with respect to x, where our limits of integration is from 0.80 to 1, since we are adding all probability values where your random variable is greater than 80%. So this is 0.80 to 1. And then the result will be integrated also with respect to y, whose limits of integration is from 0 to 0.5, since we are adding all probabilities less than 50%. So that's why our limits of integration is from 0 to 0.5. So integrating this expression of 2x plus 3y with respect to x, the integral of 2x is 2x squared over 2. And the integral of 3y with respect to x is 3yx, since y here is treated like constant because we are integrating with respect to x. So therefore, the integral of 3y, which is a constant, is 3yx. And this will be evaluated from 0.8 to 1. So substituting our limits of integration, we have 1 squared plus 3y times 1. And this will be subtracted by the square of 0.80 added to the product of 3y times 0.80. So simplifying our expressions, we have 1 plus 3y minus the quantity of 0.64, which is the square of 0.80, plus 2.4 of y. So removing our square brackets, we have 0.36, which is the difference of 1 and 0.64, as well as 0.6y, which is the difference of 3y and 2.4y. Then therefore, integrating this expression again with respect to y, we have 0.36y as the integral of 0.36 with respect to y. And 0.6 of y squared over 2 is the integral of 0.6y with respect to y. And then substituting our limits of integration, we have 0.36 times 0.5 plus 0.3 times the square of 0.5. And then subtracting by the expression when 0 is substituted, the result is 0. So therefore, our simplified answer is 0.18 plus 0.075. And the sum, which is 0.255, will be multiplied to 2/5. Hence, our probability value is 0.102. So therefore, the probability of answering correctly more than 80% of the test questions in the science test and answering correctly less than 50% of the humanities test, the probability is 10.2%. So similarly, the probability distribution of the random variable y alone from the joint probability distribution of the small f of x and y is obtained by summing all probability values over all values of x. We define g of x and h of y to be the marginal distributions of the random variables of x and y respectively. When your random variables x and y are continuous random variables, summations are replaced by integrals, because in this case, we are summing up all uncountably infinite pairs of possible values for the random variables of x and y. So these scenarios lead us to the following definition here. The marginal distribution of x, where x is a continuous random variable from small f of x and y, the joint probability distribution at xy is given by this single integral here, that our g of x is the integral of our f of x and y dy, which is adding uncountably infinite y's here. And for the marginal distribution of y, where y is a continuous random variable from small f of x and y, the joint probability distribution at xy is given by this h of y, which is the single integral of our f of x and y with respect to x, which means that we are adding uncountably infinite values of x's here. Thus, illustrating this one in an example, we will use the same problem here. The Cebu Normal University gives aptitude tests in the sciences and humanities to all entering freshmen. And if the random variables x and y are respectively the proportion of correct answers that a student gets on the test in the two subjects, then the joint probability distribution of these random variables can be approximated with the joint probability density function of 2/5 times the quantity of 2x plus 3y for all random variable x from 0 to 1 and all random variables y from 0 to 1 also. And it has a probability of 0 elsewhere from the domain above. So we need to find the marginal distribution of x. Letter B, find the marginal distribution of y. So solving for the marginal distribution of x, we need to use our definition in the previous slide, that our g of x is equal to the single integral of your small f of x and y with respect to y, because we are adding here uncountably infinite values of y's. And we know that our f of xy is equal to 2/5 times the quantity of 2x plus 3y. and this will be evaluated from 0 to 1 since your random variable y is from 0 to 1. So integrating our integrand, we have 2xy as the integral of 2x with respect to y, since x is treated like constant here. So the integral of 2x is 2xy, and the integral of 3y with respect to y is 3y squared over 2. And using the fundamental theorem of calculus, we need to satisfy our limits of integration here. So this is 2x times 1 over 1 plus 3 times the square of 1 all over 2. And this will be subtracted by the sum when you substitute your 0 in the expression. But since all the terms are having y's, then the result is still 0. So simplifying our expressions, we have 2x plus 3 halves, which will be multiplied to 2/5 here. So our g of x is 4x over 5 plus 3 over 5. So therefore, our g of x is 4x plus 3 over 5. Now, let's proceed to our marginal distribution of y. And solving for the marginal distribution of y is to get the integral of our function small f of x and y with respect to x. And we know that our probability density function is 2/5 times the quantity of 2x plus 3y. And this will be integrated with respect to x from 0 to 1. Because our random variable x is from 0 to 1. So integrating 2x with respect to x, we have 2x squared over 2. And the integral of 3y with respect to x is 3yx, since y there is treated like constant because the variable of integration is x. So substituting our limits of integration, we have 1 squared plus 3y times 1. And this will be subtracted when you substitute 0 to the expression. But since all expressions are having x's, then the result is still 0. So we have 2/5 times 1 plus 3y. And distributing our 2/5 in the binomial, we have 2/5 plus 6/5 of y. So therefore, our h of y is 2 plus 6y all over 5. Now, analogous to the definition 12, we have the following definition of the joint cumulative distribution function of the two continuous random variables. If your random variables x and y are continuous random variables, the function given by the big F of x and y, which is the probability value when your random variable x is less than the small x and your random variable y is less than y, can be obtained by the double integral of our joint probability density function of f with respect to s and then with respect to t, where your s ranges from negative infinity to x, and then with respect to t ranging from negative infinity to y, where f of st is the value of the joint probability density function of the two random variables x and y at st is called the joint cumulative distribution of the random variables x and y. And we shall limit our discussion here to random variables whose joint cumulative distribution is continuous everywhere and partially differentiable with respect to each variable for all but a finite set of values of the two random variables. Now, similar to the relationship of the derivative of our cumulative distribution function, which is equal to the probability density function of definition 9, partial differentiation in definition 15 leads to our joint probability density function here, which can be obtained by the second partial derivative of our cumulative distribution function with respect to y and then with respect to x here. So, differentiating with respect to y of our big F of x and y, and then followed by the differentiation with respect to x, we have our big F as the double integral of our joint probability density function of small f. So, integrating this one with respect to s from negative infinity to x and then with respect to t from negative infinity to y, we have our result, which is the joint probability density function of y, because the double integrals cancels with the second partial derivatives. So whenever these partial derivatives exist, as in our previous discussion, the joint cumulative function of two continuous random variables determines their joint probability density function at all points x, y, where the joint density function is continuous there. Furthermore, we generally let the values of the joint probability density functions equal to 0 whenever they are not defined in the above relationship. So, illustrating that one in an example, we have the Cebu Normal University gives aptitude test in the sciences and humanities to all entering freshmen. If the random variables x and y are respectively the proportion of correct answers that a student gets on the test in the two subjects, the sciences and the humanities, then the joint probability distribution of these random variables can be approximated with a joint probability density function of 2/5 times the quantity of 2x plus 3y for all x from 0 to 1 and for all y from 0 to 1 also, and also having a probability of 0 elsewhere from the domain stated above. Then find the cumulative distribution function of these two random variables. So first, let us define the plane properly. So our region 1 is defined when your x is from 0 to 1 and your y is from 0 to 1 also. But the region 2, as illustrated in the drawing, your x is from 1 onwards, but your y is from 0 to 1. However, your region 3 is defined when your x is from 0 to 1, but your y is more than 1, as well as the region 4, whose x and the y's are more than 1s here. So, if either x is less than 0 or y is less than 0, then it follows immediately that the cumulative distribution function of these random variables must be 0 here, since it is stated in the joint PDF above that it has a probability of 0 elsewhere. So, solving for our probability for region 1, we have our x from 0 to 1 and our y from 0 to 1. So this is the double integral of our joint PDF with respect to s from 0 to x, because we are having x's from 0 to 1. And then with respect to t from 0 to y, because our y here ranges from 0 to 1. So therefore, integrating this one with respect to s, we have 2s squared over 2 as the integral of 2s, and 3ts as the integral of 3t with respect to s, because t there is treated like constant since our variable of integration is s. So evaluating this integral from the limits of integration, we have s squared plus 3st multiplied by the constant of 2/5. And then substituting our limits of integration, we have x squared plus 3xt, because we will be substituting our x to the values of our s. And then substituting also 0 gives you the result of 0. So therefore, the integral with respect to s is x squared plus 3xt from 0 to x. So integrating again this expression with respect to t, we have x squared t as the integral of x squared, since x there is treated like constant. And the integral of 3xt with respect to t is 3x times t squared over 2. And then using the fundamental theorem of calculus, we need to substitute our limits of integration. So substituting our upper limit to the value of t, we have x squared y plus 3 halves of xy squared. And then distributing our constant of 2/5 to the binomial, we have 2x squared y plus 3xy squared all over 5. And this is the cumulative distribution function for region 1 here. Now let's proceed to the cumulative distribution function for region 2. And solving for the cumulative distribution function of region 2, we need to specify that our x here is more than 1 and our y is from 0 to 1. So we get our double integral of the joint PDF of 2/5 times the quantity of 2s plus 3t. And then integrating this one with respect to s from 0 to 1, since our x is greater than 1. So we need to add all possible probabilities from 0 to 1. And then integrating this one with respect to t, we have the limits of integration from 0 to y, since our y is from 0 to 1. So it's not full yet for all the y's. So it's running from 0 to 1. That's why our upper limit is y. So integrating 2s plus 3t with respect to s, we have 2s squared over 2 as the integral of 2s with respect to s. And the integral of 3t with respect to s is 3ts, since t there is treated like constant. And then evaluating this expression from the limits of integration, we have 1 plus 3t, since the value of our s is 1. Then integrating this 1 plus 3t with respect to t, we have t as the integral of 1 and 3t squared over 2 as the integral of 3t. So evaluating this one from the limits of integration, we have 2/5 times the quantity of y plus 3/2 of y squared here, since the value of t is y. So distributing our constant of 2/5 in this binomial, we have 2y plus 3y squared all over 5. Hence, our cumulative distribution function for the region 2 is 2y plus 3y squared all over 5. Now, solving also for the cumulative distribution function for region 3, we need to specify our random variables that in region 3, our x is from 0 to 1. We need to satisfy that our x is from 0 to 1 and our y is greater than 1. So, setting our double integral, we need to integrate our joint PDF with respect to s, whose limits of integration is from 0 to x, since our x is running from 0 to 1. And then integrating this one with respect to t from 0 to 1, since our variable is greater than 1. That is why our limits of integration is from 0 to 1, because it's full already from 0 to 1. So, integrating 2s plus 3t with respect to s, we have 2s squared over 2 as the integral of 2s with respect to s, and 3ts as the integral of 3t with respect to s, because t there is treated like a constant, since the variable of integration is s. So, substituting our limits of integration to our s, we have x squared plus 3xt. And integrating this expression with respect to t, we have x squared t as the integral of x squared, since x there is treated like constant, because our variable of integration is t here. And 3x times t squared over 2 is the integral of 3xt. So, evaluating this expression from the limits of integration, we have x squared plus 3/2 x. And distributing this constant of 2/5 to this binomial, we have our cumulative distribution function of 2x squared plus 3x all over 5. And this is our joint cumulative distribution function of your region 3. Now, let's proceed to the joint cumulative distribution function for region 4. And this can be obtained by setting our domain here, that for region 4, our x is greater than 1 and our y is also greater than 1. So setting our double integrals, we have to integrate our joint PDF of 2/5 times the quantity of 2s plus 3t with respect to s from 0 to 1. Since our x is greater than 1, so it's full for the domain of x. And then integrate also with respect to t from 0 to 1, since our y is greater than 1. So it's full also with respect to y. Thus, integrating 2s plus 3t with respect to s, we have 2s squared over 2 as the integral of 2s with respect to s. And then 3ts as the integral of 3t, because t there is treated like a constant since s is the variable of integration. So substituting our limits of integration, we have 1 squared plus 3t times 1. So the simplified expression is 1 plus 3t. And then integrating this one with respect to t, we have t as the integral of 1 and 3t squared over 2 as the integral of 3t with respect to t. So evaluating this expression from the limits of integration, we have 1 plus 3 halves of the square of 1. So the simplified numbers are 2 plus 3 all over 2, which will be multiplied to the fraction of 2/5. So this is 2/5 times 5 halves, and 2/5 times 5 halves is equal to 1. Hence, this is the joint cumulative distribution function of region 4 here, that the cumulative distribution value is equal to 1 since the two variables are greater than 1. So we can write now our full joint cumulative distribution function of these two random variables, which can be broken into 5 domains here. That when your x is less than 0 and your y is less than 0, the probability is 0 because that is 0 elsewhere. But when your x is from 0 to 1 and your y is from 0 to 1, so this is region 1, the probability is this expression here. But when your x is greater than 1 but your y is from 0 to 1, this is the probability for region 2 here. And when your x is from 0 to 1 but your y is greater than 1, the probability is this one for the region 3. But when your x is greater than 1 and y is greater than 1, the probability is 1, which can be seen as the probability of region 4 here. Now, let's proceed to our last example here. Find the joint probability density function of the two random variables x and y, whose joint cumulative distribution function is given by this expression: 2x squared y plus xy squared minus 8y minus 2y squared all over 420 for all x greater than 2 and y greater than 0. So finding the joint PDF here, we need to differentiate twice partially. So differentiating our joint cumulative distribution function with respect to y and then with respect to x. So differentiating with respect to y, we have 2x squared as the differential of 2x squared y with respect to y, and 2xy as the differential of xy squared, because x here is treated like constant. So the derivative of y squared with respect to y is 2y. That is why the differential is 2xy. And then the derivative of negative 8y with respect to y is negative 8 here. And then the derivative of negative 2y squared with respect to y is negative 4y using the power rule in differentiation. And this is divided by the constant 420. And then differentiating this result with respect to x, we have 4x as the derivative of 2x squared. And then the derivative of 2xy with respect to x is 2y, because y here is treated like constant. And the differential of negative 8 with respect to x is 0 here because the derivative of a constant is 0. As well as the derivative of negative 4y is 0 since y here is treated like constant. Then therefore, our joint probability density function is 4x plus 2y all over 420. Or you can just simplify this one by factoring the common factors between the numerator and the denominator. We have to cancel 2 here. So therefore, our joint probability density function is 2x plus y all over 210. Thus, our complete joint PDF here is 2x plus y all over 210 when your x is greater than 2 and your y is greater than 0. And then having a probability of 0 elsewhere. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to laugh your way up. Thank you.